Alrighty. Cool. I think I got everything set up. Let's make sure. Someone just mind the door, and if people want to come in, just let them in. That way we don't let the noise in. Did my OBS freak out? Is it working? Check. Cool. Yeah, it is streamed online. Does someone want to go online and let me know if my mic capture is actually working? I think it is. The Jabra is not lighting up, so I'm going to assume it is, ? All right, I see mic input on OBS, so maybe we'll just go ahead and get going. And someone stop me.
Yeah, it's working.
Cool. All right, thanks. Alrighty, so let's go ahead and get started. It's 8:35. I promise I won't keep you here for too long. You're welcome to quiz me about any of the stuff in here. But quick introduction, I'm Sahil. I used to run Warg for a little bit, and then I disappeared for about a year and a half. And now I'm back. Final year for a Tron. And today I'm going to be talking to y'all about bootloaders and over-the-air updates. Show of hands before we get into the content. How many of you know what either of those two words mean? Okay, like a little bit of exposure. Cool. So we'll get right into it. We'll talk about why you even bother with this magical thing called a bootloader. We'll talk about what an over-the-air software update actually is. And then we'll get a little bit into the weeds with bootloader fundamentals. We'll explore how you actually make a bootloader and talk about the ST inbuilt bootloader, just because it's a very bare bones type of bootloader that a lot of you will get to work with if you go into embedded software engineering. It's probably one of the most common bootloaders out there. For the Orbital folks, I know you all use TI, so you're going to have to bear with me a little bit if I use some ST-specific terminology. Now, Touch, feel free to call me out if I say something that's like ST-specific and translate. But other than that, feel free to stop me if you have any specific questions. It's more about teaching the content about the bootloader. Don't want to make it like a class or like too much of a tutorial type of thing. And we'll also discuss DFU robustness. I'll explain that acronym in just a second, where we will actually talk about how to make a robust bootloader and robust OTA. Without further ado, let's get into it. So how do you flash an embedded system? Anyone? Come on, one of you has had to flash something. I'm going to start picking on people right at the back.
Maybe like you connect something to the device and have content just like you.
Yeah, that's pretty accurate. You connect something. Anyone have a word for what that something usually is? Say it if you know it.
Flash?
So you do write to flash memory. I'm more curious if anyone knows the particular word of the thing that you're connecting to the microcontroller. Programmer? Yeah, that works. So flash an embedded system, you poke it with something, and that something is a debugger, programmer. In my world, because I mostly work with ST stuff, you have this like ST-Link V2. It's this little USB thing. That one's a knockoff, and one of them's legit. Other families call them in-circuit emulators, which do fancy things. Point is, you need to connect something external to actually flash your microcontroller. And that could be a little annoying. And so a few smart engineers said, well, what if we gave the ability for the device to update itself? So a lot of you might have smartphones, smart watches. They'll give you like a little annoying notification saying, hey, there's a new software update. Plug me in. I'm going to update myself. And in general, what they're doing is updating themselves over the air. It's wireless. Notice how for all these software updates for your phone or your smartwatch, you don't need to plug it in anywhere. You don't need to plug it into your laptop. You don't need to like attach an external debugger to your phone to update it. It just kind of says, yeah, leave me plugged in. I'll take care of it, and you wake up next morning and Siri has like 3 different voices. In a nutshell, this capability allows you to update your software and firmware remotely to customers all over the world without them needing to plug something in. And so that's really the big idea. How do we come up with a system that allows us to flash embedded systems without needing to plug in a debugger? Because we don't want to tell our customers, hey, you have to buy a $300 debugger just to receive the next firmware update to make an LED blink like 3 times faster. That's slightly ridiculous, and we want to be able to come up with a way to not do that. Now, I mentioned I would explain this acronym DFU, And just to kind of unwrap the confusion, over-the-air software updates implies that it's over the air, that you're not connecting anything to it. But the more general terminology is called device firmware update, or DFU. I'm going to stick with the term DFU because it's more general. For those of you that'll go on to work with the USB protocol, this is the terminology that they'll use. And anywhere you say DFU, that's what'll likely happen. Like, that's the term that's used. But in offhand terminology, people will also just say OTA to just refer to updating your device without the debugger, updating device using a bootloader, etc. I just want to highlight that OTA, over the air, and device firmware update, DFU, usually mean the same thing in the context. It's just that one means it's over the air, i.e. you don't have to plug a cable into it. Sound good? Cool. So when we're talking about device firmware update capability, we get a few set of key requirements. The first is that we want to be able to modify the flash memory via application software. What we're saying with this requirement is we don't want the customer to plug a debugger in to update the actual software on the microcontroller. We need to be able to write some sort of software program that will actually update its flash memory all on its own. And the second requirement is that the system needs a way to talk to the outside world. How else are you going to load outside flash in? And I'm curious if y'all have any examples of how a device can do that. Talk to the outside world to get flash in. Anyone? Yeah.
Cellular.
Sorry?
Cellular.
Cellular? Yeah, that's excellent. Any other ones? Yeah.
USB.
USB, yeah. Any more creative ones out there?
ESP, Bluetooth.
Bluetooth, yeah, that's an excellent one. I think that's some early smartwatches were using Bluetooth, I think, for their OTA. I'll take one more example. RF, yeah, generically any sort of RF algorithm. I'll give one that I saw. It was an OTA update, I think, for like those HVAC units that are like in condos and stuff. It updated its bootloader via infrared. So it was like infrared is the communication protocol that they use for the remote. So you would literally hold up a blaster and it would update. That was one that I thought was really cool. Another example that I'll point out for the Orbital folks is I understand your OTA system is using an SD card, correct? So I'm going to classify that as a way to talk to your application with the outside world, meaning you can slot an SD card in, you can store flash in that way. So you can imagine if a customer wanted to update a hypothetical system with an SD card, they can swap one SD card out, put another SD card in. So that is one way that you can talk to the outside world, even though it might not necessarily be talking. It's just someone putting an SD card in. So we have these two key requirements of device firmware update. And implementing it means that we usually need to create a separate application that modifies and loads the primary application software. For embedded systems, we're going to say that this separate application is going to run at boot, hence the term bootloader. It loads an application and it runs at boot. And that's where the term bootloader comes from. So just kind of recap, I forgot to put a question slide. Are there any questions on why we want to do an OTA and kind of the general overview of what we're doing over here? Yes, no, maybe so? All good? Seeing some thumbs up, one or two yawns. I promise we'll get into the weeds on it soon. So now we're getting into the weeds. The first thing is I've presented to you this kind of fact that I just said, take my word for it, that you can store multiple applications on an embedded system. Or more accurately, I said, you have this one application that magically can upload, store, and modify flash of another application. And the way we do that is by dividing up flash memory. So you can see over here, we have this thing called a flash memory stackup. And the way we're basically doing is we're saying we have this application with, I think, 48 plus 80, 128 kilobytes worth of flash on this embedded system. And we're going to say, well, hey, we don't need 128 kilobytes for our application. I only need maybe like 60 or 70. So in this example, I've allocated 80 kilobytes for our application. It's running in this random RAM address like 80C000 to 801FFFF. I've dedicated 4 kilobytes for some other stuff that I'll talk about in just a second. And I've said, okay, I think I can make a bootloader fit in 44 kilobytes. Now, a short tangent is determining application sizes is an art that is, kind of unknown. The best way to determine it is to just estimate it, compile a few different versions, and kind of see, okay, this is how much it is, and give yourself a little bit of buffer. But in general, the concept is that you can divide your flash like a piece of pie. You can say, okay, the application is going to get this many kilobytes of flash. The bootloader is going to get X amount of kilobytes of flash. And in doing so, we can now store multiple applications on our embedded system instead of just one. Does that concept make sense overall? It's just like storing multiple files in a folder, for instance. You can you have some storage space. You're saying, hey, so I have one application, we're going to store two.
So what's the second application?
So the second application is going to be the bootloader, which we're going to talk about in this section. But the bootloader's point is to load and update separate application software. So instead of just saying you have a microcontroller that's going to run some application, for the orbital folks, that's going to be your CubeSat. For the Warg folks, that's our flight control software. Now we're saying, okay, in addition to that, we're going to have this piece of software that allows us to update that big application piece. Yep.
To clarify, the system memory is different from the SRAM you said, right?
Yes, that system memory is just completely separate. I mostly put that in there to express that there's other addresses in the system that are not flash and that are just there. In fact, on the next slide, I'll show you a bit of what those addresses are and how I pick these numbers. But yeah, in essence, that's just addresses not in flash. Make sense? Yep.
Is there a difference between the bootloader and SRAM not SRAM, APROM or a flash? Or it's exactly the same except like flash is faster than EEPROM in general?
Yeah, so that's a good question. So I'll tell you what, I'll get to what my not limited to application software is, and I think that might answer your question. So one of the applications I wanted to present about Flash is it's non-volatile storage, meaning that if you power off and power on your device, all of the contents in Flash are still going to be there. It's a little annoying when you try to write your application in volatile storage. That means that you have to reflash it every single time. Fortunately, with flash memory, you don't have to do that. You can trust that if you power on your device, the application is still going to be there. But another use you can do is use a section of flash, in this case 4 kilobytes, as emulated EEPROM, meaning you can just use it as non-volatile storage. You can store whatever you want in there, like random constants or whatever, a password, whatever you want to do, and you can swap it out on the fly in your application. So with Flash, actually, on the next slide, we'll discuss its limitation. In particular, you can only erase it in blocks, but I'll save that for the next slide. One caveat I do want to point out is that if you want to store multiple applications, you need to make minor linker script and register modifications. I don't want to get too into the weeds of how to do this. Just make sure that if you're going to write a bootloader, look these two things up for your chip. It's going to take you maybe 20, 30 seconds. Look up an example, do it. Just remember that caveat if you ever want to write a bootloader. Sound good?
If we make a STM project and the L file, does that already contain the linker script and register modification?
Yeah, so the question is like if you make a default project, Higio gave the example of an ST project, but even for TI, Code Composer Studio, I think it'll produce like a linker script, startup script, all that stuff for you. Is that correct enough, Tush?
Yeah, I think Halpigen produces that stuff.
Yeah. So in general, if you have like some sort of code generator for your embedded system, it's going to give you a linker script. Again, that linker script is going to assume you have one application. You need to make a slight modification to it called defining linker script regions, which is a trivial thing to do. Just look it up on how to do it. You just basically say, oh, instead of 128 kilobytes, it's 44 kilobytes. And that's about the extent of the linker script modification. Cool. So moving on to what I promised I'd talk about, which is a tangent on flash memory control. So flash can usually only be erased in sectors. So with that 4 kilobytes I mentioned earlier that you can use to emulate EEPROM, it's all or nothing. If you want to write something to it, you have to read all the contents in, erase that entire 4 kilobyte bank, and then write to it. You can see that's a little bit annoying if you don't want to store 4 kilobytes worth of data. For some context with EEPROM, your constants might be like a couple of bytes. So needing to erase and write 4 kilobytes is total overkill. Flash can only be erased in sectors, which is its primary limitation. That's why embedded systems will typically use EEPROM for constants that have smaller size. And one thing to note is that erasing flash is measured on the order of seconds. So if you ever try to flash an embedded system, you'll notice it takes like 2 or 3 seconds. That's because it takes a lot of time relatively to erase that flash and then write to it. And then, like all non-volatile memory, flash memory can wear out if excessive erasing and writing occurs. So that's just one thing to be aware of with your bootloader is don't try to constantly spam write or erase flash because you'll wear it out pretty fast. And one thing I also wanted to talk about was sector and page organization. So going back over here, I just kind of pulled these like sector numbers out and I said, here are some sizes. This is the data sheet for that exact microcontroller. And you can see you have these like sectors. Sector just represents a unit of size of flash that we can control. And in this case, the data sheet is basically telling us, well, sector 0, I can erase 256 bytes, 256 bytes. Sector 1, I can only erase in 4 kilobyte segments. And then sectors 32 to sector 33, I can only erase in 128 kilobytes segments, if that kind of makes sense. It's just kind of telling you the lowest possible unit of flash that you can erase or write to. Clear? Any questions? Haziness? All right. Before I put you all to sleep, let's move on. So a question that you might ask is, how do you run an application not at the base address? And to clarify what the base address is, it's this number right over here, this 0x8000000. That is the address that the embedded system is going to first boot at. But clearly this application is not at that address. It is some 48 kilobytes above that. So on boot, the hardware is going to look at 0800 and try to run something called an application reset vector. But our application that we want to run is not located at that 0x0800. It's located above that. And so what we want to do in our application is develop a way to call the primary application's reset vector within the bootloader. So hardware on reset is automatically going to call reset vector. You can see on here, this is the address for the ARM vector table. Can you all read that in the back, any chance? No? Got to split. I promise you this says 4, and this offset of 4 is going to come in handy in just a slide next, where we discuss how to actually call the reset vector. But in essence, this basically describes the available interrupt vectors that an embedded system has. Show of hands, how many of you are familiar when I say the word interrupt vector? Okay, well, let's explain that first of all. So an interrupt vector just basically describes the addresses or functions that your hardware can call when it receives an interrupt. So how many of you, for instance, have worked with like a GPIO interrupt or a timer interrupt? Raise your hands. Cool. In that, have any of you had to define this like function that's like GPIO interrupt callback or something? Yeah. So in essence, that's the hardware basically saying, okay, I have a GPIO interrupt on line 32, and then it calls that callback over there. The interrupt vector table is basically just a table of all those function addresses that the hardware calls for you. That's why when you define those callbacks, you're just basically telling the hardware, hey, if you receive a GPIO interrupt in this example, go call this particular function. So we extend that to the reset vector, which is basically saying, well, on an application reset, I want you to do this one very particular thing. Yep.
You're not sharing your screen in PC.
Ooh. Thanks. I don't think anyone's watching, but...
Somebody messaged asking if you're not being presented.
Oh.
I think they saw you in there.
Oh. Thanks for reminding me. Cool. Anyway, so applications are started by calling its reset vector. We're familiar now with the concept of an interrupt vector table, which is just basically calling this magical address. And the reset vector calls something called start or cint for TI microcontrollers. And all it does is it basically does the relevant setup before calling main, like zeroing out RAM, doing all your constructor setup if you're working in C++, etc. Tangent that I have in the slide link, and an interview question that I've gotten a few times is, what happens before main is called? The answer is start with the reset vector, because that's what the hardware is going to call for you, and then look this question up and then figure out the answer from there. There's a good link that I've left in the speaker notes that basically explains the full processes, which is basically like, zeroing out RAM, initializing clock trees, etc. But it can be a bit of a rabbit hole to go down. That being said, good interview question. Recommend knowing the answer to that if you head into embedded software interviews. Any questions on reset vectors in particular? Yeah?
Yeah, so just want to clarify.
Mhm.
Reset vector code every time you do that specifically, or every time you run every time you run it, C file?
Yeah, so that's a good question. So for in embedded systems in particular, the hardware is basically programmed to say on a power on reset, go straight to the reset vector at 0x0800 or whatever the base address is for your microcontroller. And that's why we basically want to have an application down there that says, okay, well, if a reset happens, I want to decide what happens next. And in our case, our motivation is we want to run an application that isn't located at 0x0800. In the case of a hard fault or something similar, it may also choose to call the base address reset vector again. And we'll actually talk about that and how your bootloader can handle a case where your application's hard faulting. In essence, though, anytime the hardware wants to reset or you hold down the reset pin on a microcontroller, it's going to call the reset vector of whatever application is at the base address. Does that answer your question? Cool. Yep.
What is the negative value of priority?
Good question. I don't actually know. And that's the same question I had. I wasn't sure if that's higher or lower priority. Though he was asking what the priority means. This is an ARM standard, not an ST standard. So I don't actually know. I haven't delved that deep into the ARM standard. Yeah, sorry, I don't have the good answer for you.
All these addresses for reset and stuff do ST when we're flashing it initially. How are these stuff going onto the flash?
That's a good question. So if you're flashing it with a debugger, the debugger basically just sidesteps the entire core execution process and just writes the contents directly to flash. Our motivation is to basically do that ourselves without the debugger. But I guess to say is that the reset vector is something that's contained by your microcontroller, just contains a table of addresses, and those table of addresses are defined by your program. So inside your program, you're basically saying, well, for a GPIO interrupt, for instance, do this. It's just that for things like the reset handler, hard fault handler, that's already given for you, but it's defined on a per program basis. Does that kind of make sense? Cool. And now to tie it all together, all we have to do to load an application is to call its respective reset vector. And so we make a function pointer that is at the application start address +4, because that's the offset of the reset vector. So coming back to this table where I mentioned that 4 would be a little bit relevant, you can see at 0, it's just reserved. I remember looking up at some point, some ARM reserve standard does something with it. But the reset vector is at 4 bytes away from the actual application address. And so what we have to do is we just basically make a function pointer saying, okay, at the application start address +4 bytes, we're just going to call it. And magically, through the magic of C and your microcontroller, it's just going to go ahead and call the application reset vector, and it's going to boot into your application. Does the general concept make sense? Like going from this thing saying, okay, we have this magical function in each application called the reset vector that we can call, and just saying, okay, we can just call that in our code arbitrarily. In the back?
And then what happens at address 0? Isn't that supposed to be what the first instruction is, to be executed?
Oh, I think I remember now what it is. I think it's the stack pointer. Or, okay, I'll look that answer to you at the back, but I'm pretty sure it is the stack pointer. I just don't want to misspeak without looking it up first. But I think you're right. It is something like that. That's why it is the first thing. Any other questions? Yep.
How does the reset pointer actually understand where's the application start address?
So that's the thing that C will let you do. So C is a very unsafe language. It's willing to let you turn all of this, whatever. It's going to assume that you know what you're doing. So you define this application start address. The compiler is probably going to spit out a few warnings if you type this right in saying, hey, what are you doing? You're just randomly casting this integer into an address and letting me call it. But C will let you do that because it's an unsafe programming language. So it's up to you to make sure that it'll do it. The microcontroller is more than happy to let you call any arbitrary address, including null. So you're more than welcome to try calling a function at 0x00. You can try calling a function anywhere. And if you do something wrong, the microcontroller will freak out at you and give you a hard fault, saying that you're not allowed to call that address.
So how does that next time after you want to re-enter the bootloader, actually know where the address is of bootloader?
So the bootloader is contained at the base address.
So you're rewriting the reset
Okay, so that's a good question. We can talk about this vector table offset briefly then. So in essence, every application has this thing called the reset vector. We've figured that out so far. Every application has this interrupt vector handler. On reset, what it's going to do is it's just going to call it straight at the base address. It doesn't actually look at something called the vector table offset, which is basically saying, hey, if you receive an interrupt or anything else, instead of calling it right at this base address, offset it by, in this example, 48 kilobytes. If you do have a power on reset or some sort of boot loop, the microcontroller just completely ignores that. So it's a special exception for reset cases, if that makes sense. For any other case, if you don't define this vector table offset, it's going to try to call your interrupt vector handlers in your bootloader instead of the interrupt vector handlers that are defined for your application. Does that answer your question? Yep.
Well, I was just gonna say for like us for TI, the reset vector is right at 0, so there's no offset of 4.
Is TI not? Is your standard not ARM?
It is ARM, but it's ARM Cortex R4. It's a rare ARM.
I know this is defined as an ARM standard, but maybe it's not defined for whatever standard you're doing. In essence, though, always look up these like particular quirks for your particular chip. Datasheet is your friend when you're writing this kind of low-level code, just to make sure that you kind of understand what's actually happening under the hood. Yeah. Any questions on how to run an application not at the base address? Okay. So what we've built up now is a tool to run arbitrary applications. We can basically say we have an embedded system now. We can have 2, 3, 5. We can have as many applications as we want running into it. And now we have the ability to just call those applications at will. Because if we know where its reset vector is located, we can just type in a little function in our program, run it, and say, cool, we're going to run that application. And so what I'm curious about now are your thoughts on where these scenarios could be useful, where you're loading arbitrary applications. Any thoughts? Anyone? Crickets? In the back?
Like any device that has multiple apps, like your smartphone.
Yeah, that could be a good one. So if your device like inherently has 2 different applications that you just don't want sharing like the same code base or anything or whatever, maybe you have like 2 different like flight control algorithms that you just want completely separate, you can just switch between the 2 and have completely separate applications. They don't know about each other. The only consequence of that is each application now gets less flash space available to it. But that is an option, yeah. That's a good one. Did you read my slides? Cool. Okay, that's my next one. Any other ones before I dive into that? Okay, so one Yuchen, right? Cool. One that Yuchen mentioned is flash integrity. So you want to make sure that you don't load corrupted software. So your CubeSat, it's in space. I'm assuming it's going to get doused with a crap ton of radiation, eh? So you have flash all over there. It's being doused with all this radiation, and maybe a bit flip occurs somewhere in there. And maybe that bit flip occurs right in your GNC code where it says, okay, if true, tumble the CubeSat constantly, which I'm going to assume is a bad thing for your CubeSat. For the work kids, just assume it's like, okay, if true, just roll the plane constantly. And that can be bad. We don't want to do that. We want to make sure that whatever application flash we load is actually the flash that we compiled it to be. Now, coming back to that comment I made earlier where flash memory can be susceptible to bit flips or it can wear out if it's written to repeatedly, it's common for a loader to verify the application's integrity before running it. What that basically means is we want to basically check over the application flash and say, hey, we are running the same thing that we were told to run. And the way we're going to do that is have a checksum or some sort of other data integrity check like a CRC and store it alongside the application. And every time we want to launch the application, we're going to do a quick check, compute the checksum live, and then compare it against the stored value. Now, if there's any sort of bit flip or anything, either in the checksum or in the main application, those 2 will not match. And then we can say, hey, we think something's sus with the flash. Don't run it. And we can now do something about it. Now, what you do about it is entirely up to you depending on your application. Most applications are just going to say, hey, stop. We're not going to do anything. We're going to wait for instructions. Other applications might have some sort of safe mode, but we'll discuss that in the later slides about device firmware update. Any questions on this particular loader consideration? It's probably one of the most common reasons to have a loader, not just something that can update Flash. Like in a lot of safety critical applications, you will literally just have a loader where its only job is to check Flash integrity. It doesn't bother doing updates. Yeah?
Do people normally do CRC when you transmit stuff onto a bootloader Flash?
Yes, and we'll talk about that when we talk about transmitting stuff into bootloader Flash. Any other ones? Cool. Another one that you can do is catch a boot loop. So a boot loop is basically, your application does something dumb. It tries to dereference a null pointer because C will let you. And, it's a bug in the application code. And it will trigger a hard fault. And normally, this hard fault will usually reset the processor, which is going to end up in which application? Bootloader or main application? Any thoughts? Hands up for bootloader? Hands up for main application? Cool. All of you raise your hands for bootloader that did. So you'll end up back into bootloader if you hard fault because there's an exception for that particular reset vector. And in this case, you haven't lost power. And so a common technique to catch a boot loop in your bootloader is dedicate a section of RAM that the bootloader doesn't touch and the application doesn't touch unless it catches in a hard fault. If it's in a hard fault, it just freaks out, writes in a persistent RAM to bootloader saying, help, please, something's wrong. And the bootloader, when it comes back in after the hard fault, it goes through its reset vector. You can tell it to read this particular section of persistent RAM and say, hey, application said it was not having a good day. And then from there, you can choose what to do, which can include trying to run the application again for as long as it takes. Maybe you say, okay, the application can run 3 times. And if it hard faults 3 times, we're going to say no more. We're going to stop running that application. Or maybe you switch over to another application, or you just stay in the bootloader. It's your choice what you want to do, and that's a system design level question. But I wanted to highlight that your bootloader can catch a boot loop if you want to architect it right, and you can make your bootloader do whatever it needs to do to basically prevent running faulty application software, even if there's a bug in the application. That concept makes sense? In the front, yeah? It depends on how the watchdog actually did. So for context, the question asked is, can a bootloader detect a watchdog reset, which is basically like the application was taking too long and didn't feed or pet the watchdog in time? And it depends. So if you have an internal watchdog, oftentimes there's a hardware-specific flag that's written, or like a bit you can read, saying, hey, the watchdog freaked out. This is why it reset. There's also hardware-specific reset flags for power on reset and software reset. Software reset is usually code for hard fault, but double check your exact microcontroller for that implementation. If you have an external watchdog, it gets a little bit trickier. Maybe that line is just asserted and never cleared. It depends on what particular watchdog you're using. But if it's an internal watchdog, usually there's a bit in there you can read. And that'll basically tell you, hey, the watchdog freaked out.
I was going to add, if it's an external watchdog as well, it's still going to need to reset it some way. That can be either through a pin or through, just powering it off. So looking at the reset flags might give you a hint. If it says it was turned off because the power reset pin was asserted low, then that gives you an idea that it was probably the watchdog, unless it just magically got asserted low.
Yeah. So yeah, it just basically depends on what hardware you're using and checking the hardware-specific flags. Cool. Any questions on these particular things for loaders? No? Alrighty. Not all of you are asleep, so that's a good sign. So we're going to get a little bit into the weeds now when we're discussing device firmware update. And we now have a way with the bootloader to basically say, okay, we got multiple applications. How do we load them? And that can be useful. I mentioned the application where, in aviation, that's kind of my background. You have this loader where its only job is to say, hey, is the flash good? And then load the flash. It doesn't actually deal with updating in a lot of cases. But for a lot of embedded systems, we want to say, okay, we want to actually update this. And so ultimately, in a system with DFU, we want to be able to swap out sections of flash with new data. And that new data is typically our new firmware image. Importantly, this data needs to be correct. We've discussed the consequences of what can happen if you load bad or corrupted data. And I've written the definition of incorrect data. And in general, what I want to leave you with as we're discussing the device firmware update for ST is try to think of edge cases. One of the important things that we'll discuss about later is what happens when your DFU system isn't robust. And in general, the complexity of your DFU system is going to increase with its need to be reliable, just because it's going to be one of the main things that you use to actually update your software. You can imagine right now, if all of your phones, all of your laptops, the updater just broke. Like imagine CrowdStrike. It's kind of similar in this case. If your bootloader screws up, it's going to be a very similar situation to CrowdStrike with all of your products. So be very careful with how you manage a DFU system, because chances are it's shipping on every single one of your products. Just be careful and try to poke holes in the implementation that we'll discuss in the following slides. Any questions on the actual DFU problem and how we're going to define it? Yeah.
Do we have a clarification on the difference between bootloader, DFU, and BIOS?
Okay. I can't really answer BIOS to you. But what does BIOS stand for again?
Basic input output system.
Thank you. Yeah, so I can't clarify BIOS for you because I don't know much about it, but I can clarify you the difference between a bootloader and DFU. So to come back to the front, a bootloader is a piece of application that's going to run on boot that will allow us to run different applications. And DFU is now saying, well, now that we have this piece of software that can load random applications, how do we swap out this main primary application? Does that difference make sense? Any other clarifications I can make? Hardy?
What's the difference between the bootloader and the programmer? Is it so if you have a programmer that we don't need a bootloader?
That is, sorry?
Or we still need it?
So yeah, that's a good question. So our goal with DFU is to basically update the software without a dedicated debugger. You still need a debugger if you want to actually debug your system, because that's a hardware-specific feature. But the goal with device firmware upgrade is to write a piece of software to eliminate the need for a programmer to actually program your chip. So the goal isn't necessarily to be able to replace a full debugger in the sense that you can debug or set breakpoints. The goal is to basically be able to say, hey, we can just upload this random flash and run it without a specific programmer, using however way the device actually talks to the world. Make sense? Cool. I'll take a yeah.
Also, another question is, how do we load the bootloader?
How do we load a bootloader? That's a good question, and one I probably should have clarified in the slide. So the bootloader is the one thing you need to actually flash with the debugger. And so oftentimes if you're working on a commercial system, what you're going to end up doing is sending out your first bootloader image to the fab house or wherever and saying, okay, this one time you're going to connect a debugger to flash the bootloader. But that's the only time you end up needing to connect a debugger to. One more?
Does DFU reside in bootloader section or is...
So that's a good question. Does DFU reside in bootloader section? I'm going to discuss an implementation where it does reside in the bootloader section, but it doesn't have to. Your application, you can in general have two applications in your system, both of which can have DFU capability. Thing is, now you add risk where you still need an application to run at boot, and you still need something to say, okay, well, what application are we going to run? And that typically is handled by a bootloader. And so as a result, a lot of embedded system implementations lean towards putting their DFU capability right in the bootloader itself. We can discuss self-updating bootloaders after this, just because it can get a little bit complicated with that regard. But in general, for embedded systems, you put in the bootloader because that's the thing that decides what application you're going to run. And as a result, it makes it easy to swap applications in or out. The other thing to note is that if you put your DFU thing right in an application, say if, Random Co-op adds a bug into your DFU application or into an application that will be uploaded via DFU, and that is the thing that also is responsible for your updates, well, guess what? You might have just bricked the ability to update. Now, one of my friends did that at one point at his company. So just be very careful with putting DFU capability in an application. They can't swap in or out easily. It means that it's very easy to accidentally brick your system. And that's because on a lot of commercial systems, your bootloader and your DFU system is actually the only way to program it. You actually lose your debugger and programmer on a lot of commercial systems because they lock it out for you. Any other general questions I can answer about DFU?
Maybe not quite on embedded systems, but I know for some systems like Mac OS and iOS, they have multiple levels of bootloader. So like for Mac OS, I think it's like 2 or 3.
Mm-hmm.
Is there any advantages to that?
Yeah, absolutely. Tell you what, why don't you ask your question right at the end once we discuss a DFU system? Because multiple level bootloaders is advantageous in certain regards, but let's first discuss a DFU implementation and then we'll come back to that. Sound good? Cool. Any other ones I can take generally? Alrighty, we'll get into the weeds. The first is defining the DFU from kind of like a flow chart. Yep.
There's a question online.
Ooh, can you read out to me?
Looking at the definition of OTA, when do you need a debugger to upgrade firmware?
When do you need a debugger to upgrade firmware?
Yeah.
Okay. So the goal with OTA is to remove the need to actually have a debugger to update your software. Is that definition clear? Like, is the motivation of why we want to do DFU clear to y'all? Any chance I can offer clarification? Okay, sweet. So basically the entire goal with an OTA or DFU system is to remove the need to connect a programmer to our system to actually update its flash. So ideally, if we do our jobs right, if we have DFU capability, the only time you need a programmer is to flash the bootloader. Does that answer their question online? Let me know if they want clarification. But that being said, sorry?
Sorry, a follow-up clarification on that. Like,
Yep.
is the bootloader ARM-specific dependency or is it manufacturer dependency?
So you're the one writing the bootloader. It's you write a bootloader typically targeted to a particular microcontroller.
Sorry, the debugger.
Oh, debugger?
Because the question will be the same company that you have to actually flash the flash,
Right.
actually putting it like to a hub and flash it over SPI.
Yeah, so if your debugger is typically microcontroller specific. So if you're going to make like a product that's running out a particular microcontroller, you're going to use a debugger that you can. So like, SWD for ARM or a JTAG debugger if it has it. But in general, whatever debugger you're using for your microcontroller is what you'll use to actually flash the bootloader.
So
But
there are some microcontrollers that you have to flash it directly through flash, not
yeah, that's correct. Some of them can also use, they flash over SPI or wherever. The entire goal with DFU or OTA is to basically remove the need for an external debugger. And so that's what we're discussing. Cool. Oh, in the back right over there?
Just to clarify,
Go for it.
bootloader tells what application to run.
Yep.
If you want to swap application.
So the DFU is how we want to swap out sections of flash with new data. So think of it as though we've got our bootloader, we've got our application, but we want to run a new application on it, right? Say we have new flight control software that we want to update. So, one has really bad tunings. We're like, no, we have a different image that we want to upload. And so if we implement a way for our system to basically update that flash, we just go in and we say, okay, we're going to take out this existing application. We're going to overwrite that section of flash with our new image, and implementing that process is referred to as a device firmware update system. That clear?
Somebody online asked from the last question for clarification.
Mhm.
They said, I see when you say debugger, are you referring to an actual developer who needs to flash new code onto the microcontroller? Or the goal is to remove developer from the equation for upgrades? Question mark.
So when I say debugger, I'm referring to these big bricks over here, like a physical debugger or programmer, not necessarily the developer. All right. I will get back here. So back to the flow chart of actually swapping out application flash data. So can you all in the back actually see this flow chart? Yes, no, thumbs up, thumbs down? Thumbs down? Okay, we're going to do it this way. Can I zoom in? All right. Is that better?
Yes.
Cool. So let's cover the points first. Just going to make sure. Okay, it's actually just this flow chart. So we start off by defining how we actually want to start an update. So if you think of your phone, maybe it's pointing at you with an annoying pop-up saying, leave me plugged in. I'm going to update at 3 a.m. tonight. Some other devices are going to say, hold down this button for 5 seconds to begin a firmware update. first thing is you, as an engineer, need to define how is my system going to actually update. I figure for your CubeSat, you don't want to send someone up on a satellite to press a button down for 5 seconds to say, hey, accept a new software update. It's probably going to be something like, okay, send a command to actually update the software. So that's the first thing you need to do. You need to figure out a way that makes sense in the context of your system to actually start a DFU process. And I've included in here target flash erase. This isn't always true, and we'll discuss an alternative slightly after, but in a lot of systems, you typically erase the flash of the application that you're going to replace just because there's limited RAM to store a full image. And it's usually just easier to basically say, oh, you want to load a new image, just get rid of the old one, toss a new one in. There are ways you can get around this on more advanced system designs, but for a basic DFU system, we're going to discuss it this way, where the target erases the flash, and then it's going to write a new one from a host. So we start off, something says, okay, you've held down a button for 5 seconds, you've told it, okay, it's 3 a.m., we're going to start updating. The target erases the flash, and DFU target now downloads a binary from this thing called a DFU host. Did I define these terms? I did not. Sorry, I thought I had a flowchart here defining DFU host and DFU target. My apologies. DFU target is a device that you're actually updating with new flash, so that's your microcontroller. DFU host just refers to something that's hosting the application image. It can be an Amazon server, it can be your ground station, it can be your your laptop that you're connecting to over USB. As long as it has the target image in some way to communicate to the target, we're going to refer to that as a DFU host. DFU target is just simply the device that's actually undergoing the update. Think of it as the microcontroller in a general system. Those two terms make sense? Cool. So back to where I was at. Target's going to erase the flash. DFU target is going to download the binary from the DFU host and write it to flash. After which, we're going to tell the target, hey, let's make sure we actually wrote all of those flash bytes correctly and check if it's valid. And if it's not valid, we're going to try to see if we can handle that error. And if it is valid, then we're going to say, okay, maybe we jump to the app directly, or maybe we load the software in a couple of hours. Flowchart overall makes sense? Cool. It is pretty straightforward at the end of the day when you're implementing DFU. It's actually more of a communication problem than it is a, how do you actually sort bytes, etc. Because your goal is simply to be able to get the image from the DFU host to the DFU target flash in one piece. That is all a DFU problem really is at the end of the day. Everything else is just making sure, okay, how do you actually start it? What do you do if the image isn't valid? And what should you do if the image is successful? Those start and end points make sense? Yeah?
Well, I was gonna put you could also, for us, we'll probably, instead of erasing the flash before you start downloading the image, download the image and buffer it on something like an SD card. And then once you're ready to actually load the image, then do the reset erase the flash.
You're going to force me to jump right over here. So what Navtaj was going to steal from me is I wrote an example of OTAing with an Amazon AWS server. You could pretend that's a ground station for y'all orbital folks. But in this case, I'm saying, okay, something's going to tell you to download an image over here. Can everyone in the back still see this okay? Cool. You're going to say, okay, something's going to tell you to download. Maybe it's a ground station command. You have this AWS server with an image. It downloads it, writes it to an SD card. We verify the downloaded image, make sure the image is valid, and if it's yes, we just end a download. And in this case, if it's not, I just say, oh, just try to re-download it again. And when we want to load an application, we just take the data from the SD card, overwrite the application flash with the new SD card image, and then we verify the flash image. And if so, we're going to launch it. That makes sense overall. There's different ways how you can define loading a DFU host flash to your actual target flash. Make sense? Cool. So going back over here, I promised we'd talk about the ST bootloader, but for brevity, maybe I will just go over the broad strokes rather than discussing depth by depth. So have any of you worked with the ST inbuilt bootloader by any chance? No? Okay. For context, this is basically the inbuilt bootloader that ships with just about every ST microcontroller. It usually supports UART, I2C, CAN. If you're ever working with any ST microcontroller, it's usually a peripheral that's supported. In this case, I've chosen to break down the UART STM32 bootloader. And it starts by just basically saying, hey, if you send this 1 byte 0x7f over UART, I'm going to enter bootloader mode. And that's how the inbuilt bootloader starts. And after that, it just patiently waits for commands. And it's summed up pretty nicely in this flowchart right over here. And that's just basically how the bootloader process ends up starting. You can think of it back in that general flowchart as saying that's the DFU start request. Yep.
I think one time I read STM data sheet, there's a dedicated boot pin. Is that exactly the same one that you're referring to?
Yeah, so the question is, on a few microcontrollers, there's usually a dedicated boot pin. And yeah, so oftentimes with this boot pin or boot pins, it's gonna let you kind of pick where you want to start booting from. In the case with ST, if you set the boot pin low or boot pin high, it might go to the internal bootloader instead of system memory. So a lot of chips actually come with a bootloader for you that you can use. It's usually not sufficient for a lot of applications, but for a lot of applications, you can just straight up use it. It'll usually work. Lots of libraries to go for it. But yeah, the boot pin controls where you boot from, and one of those options is typically an inbuilt bootloader.
Go ahead.
Yeah.
That is a totally different concept than using SWD from the debugger side to flash.
Correct. It's completely different from using a debugger.
Yeah, I was gonna ask, what if you're like in your application? Is there like a way to invoke the bootloader to run with the SD bootloader?
The inbuilt bootloader, I'm actually not sure if you can invoke the inbuilt bootloader from your application. I can Google it, but that's probably the best thing I could do. I'm not sure if you can do that with the inbuilt bootloader because it's just like on there. It's in hardware. Maybe is the best answer I can give you.
So when you want to do an update with ST, does it just reset the thing?
So typically with the inbuilt bootloader, you need to reset it and then spam this like UART byte over to it, and then that's going to put it in bootloader mode. Yeah.
What's the difference between UARTs and USARTs?
Okay. So it's a bit of a tangent. The question is, what's the difference between UART and USART? One is synchronous universal. It's universal synchronous asynchronous receiver transmitter. The other is universal asynchronous receiver transmitter. Basically means that one of them has a clock line, one of them doesn't. It's a little bit out of scope from this, but in essence, if you're familiar with the difference between SPI and UART, USART is basically a SPI version of UART. Does that make sense? Google it if you'd like more information, and I have an article I can send you on exactly this topic if you want to come up later. Yep.
So why would you need to like go to the bootloader that way by plugging in like a cable and then sending that message from USART as opposed to using a debugger?
Yeah. So the question is, if you're a customer, say if you want to update this like Jabra speaker over here, it's a lot easier for me to just plug in a USB cable and then go into some tool and say, okay, I want to flash, than it is for me to have to buy this $300 brick to plug in and then upload a particular image. Debuggers are engineered for us developers. They're engineered for us to basically say, okay, we want to be able to set particular breakpoints, we want to be able to upload flash, etc. The fact that it can program is one of its functions, but it can also do a lot of other things. But for our customers, we want the experience to be simple. We want the experience to be intuitive. We want it to just be able to work anywhere. And more importantly, for your CubeSat, you don't want to send someone up into space with a debugger to upload a new image. You just want to be able to send something from the ground to actually update it. So it can really depend on the context, but that's generally why you want to do an OTA, is to eliminate the need to use a dedicated programmer. That makes sense?
Yeah.
Cool. Over there.
So like, does the inbuilt bootloader get overloaded when you upload your bootloader?
No, actually. So the ST inbuilt bootloader is another application that's hiding beneath flash memory. So you can think of it as though if you have your own bootloader and an application, there's a third application right there, and that's the ST inbuilt bootloader hiding right beneath your bootloader and flash. It's basically an area of flash that you can't access. It's just always there. You have the option of not using it, you have the option of using it, but it's always there. So it comes back to that concept of in embedded systems, you can have as many applications as you want. You just kind of pick and choose which ones you actually want to run.
Wait, so is the inbuilt bootloader in ROM, so I can't get rid of it?
Nope, it's in ROM. So that's why it's a choice to use it. It's popular for this reason because it just works. It's robust. There's a lots of tooling for it, and that's why I'm presenting it as an option here. But rolling your own is also an option, and for most systems, you'll probably end up doing it.
So if we're going to use a team bootloader like this flowchart showing here, so we need to, upon a startup, immediately send like 0x7f to request it to bootloader.
Correct. Yeah, so typically what you'll do is you'll hook up one of your lines to basically reset the chip, and then you'll hold it and reset some pin combination, and then you'll spam 0x7f. And as soon as it receives it, it'll be like, oh, yep, I want to bootload. Cool, we're going to go into bootloader mode. And then you can run these commands that we'll discuss in just a second to basically write and reset the flash. Yep.
So I see a one data shelf STM that does support using UART to flash, I2C and SPI to flash, and there's a DFU through USB. Like, what's the difference of directly using UART and all those protocols and USB DFU?
Convenience. So the question is, the STO inbuilt bootloader supports a wide variety of protocols. Off the top of my head, CAN, I2C, you mentioned USB, UART. Question is, why would you use one over the other? The simple answer is, what is your system using? If you're non-automotive, typically the only way to talk to your chip is CAN. Like, what are you using for your communication protocol? Like some sort of RF thing over UART, SPI?
Or
your CubeSat.
Our SD card is through SPI, and then ground station link is RF.
Right. So the only way to talk to your chip is through this RF link, presumably, correct? So if that's the only way to talk to your chip, then that's just what you're going to have to use. Aside from that, it's convenience, depending on what method or what communication protocol you use for the inbuilt bootloader. But I don't want to focus too much on the specifics of the ST bootloader itself, just more on how the bootloader kind of implements its functions. And I want to just kind of go over the commands. I was going to go in depth onto them, but for the sake of time, I will jump over. They're in the slides if you want to go into the depths of how they actually work. But this will suffice for now. And the key commands that we're interested in are write memory. And this is the key part. We can basically say, okay, we have this image over here that's on our host, and we want to be able to write it into flash memory. And this write memory command, 0x31, means that we can basically write up to 256 bytes in a single transmission to a flash memory starting from an address that we specify. And so, yep.
Why 256?
Ask ST. It's just a limitation that they've set, 256 bytes. Yeah, they're the ones who can give you the answer to that question. But yeah, anyway, you can write up to 256 bytes starting from an address. If I'm going to guess or speculate, my guess is that that's probably the size of a page that it can erase. Meaning, like, if going back to an earlier slide where we talk about sectors, if you go back over here, actually, I'm going to bet, 256 bytes is the size of a page. So I'm going to bet that that's just the minimum size they can write to. But yeah, it would depend on the specifics of the bootloader, but that's generally how it goes, as that's the size that you'll end up writing. Make sense? Yeah. And then the other command that we want to go to is basically erasing flash memory. So if you remember at the start of DFU, the method that I presented is if you want to start the DFU, you first erase all the flash, and then you write it. So you might first go, okay, you send this erase command of 0x43. Then you go ahead and do write memory 0x31. You write all of the amount of bytes that your application image has. And then you just basically say, okay, we're going to write a go command of 0x21 and actually jump to that application address. Yep.
Is it actually a good idea to read protect your bootloader?
So, sorry, say that again.
Is it a good idea to read protect your bootloader?
Read protect. So I haven't looked into this command in particular, but read protection generally implies that if you enable it, people can't read the contents of flash. And generally, if you're in like a commercial environment, you don't want people stealing your code. You don't want people disassembling it. And so implementing readout protection is what you'll do just to make sure that people aren't basically stealing your code and trying to be like, oh, this is how this system works. You got your special sauce in there. You're making money off of this product. You don't want people knowing how your code works typically. So if that's the case, readout protection is what you'll want to implement.
Write protect is here to prevent memory corruption.
Write protect, I believe, and I'm going to talk a little bit out of my butt just because I haven't read it, but readout protection is going to prevent you from reading contents of Flash. Write protection is also going to prevent you from actually writing to that Flash sector. So they both kind of work in conjunction. One and the other, they both kind of work together. One is to make sure people can't read your content. The other is to make sure people can't take over your Flash, which is an important consideration in a bootloader.
Do you know what the get checksum command would be useful for?
Yep. So actually, that is so if we actually go back to the loader slide right over here. So the get checksum slide is used to actually implement this Flash integrity function that we were talking about. So say if we don't trust the internal bootloader, we want to do the checksum computation ourselves. We might have our own version of the image that we think we've sent over to the chip. We'll calculate our own checksum, and then maybe we'll just ask the chip to send it its version of the checksum. And if those two match up, then we'll tell it to go on. So presumably that's an option that you can take as well from the host. Cool. Other than that, I just want to kind of highlight, I don't want to go too into the weeds of the S2 bootloader. I was originally going to talk about them, but in the interest of time, maybe we'll jump over. But do you all kind of understand the key commands that we're interested in? Erase, write memory, and go? Can I get some nods? Fusion in the back over there?
I sort of missed part of the slide. So
Mhm.
isn't it that after we set, like, for example, 0x7f to tell that the microcontroller that we're in DFU, are these the commands that we send to tell like what to do, like in terms of picture reads?
Correct. So if you look at this flowchart over here, we send 0x7f to run into bootloader mode. Then we're going to wait for a command, and those are the commands that we can send the bootloader to basically be like, hey, I want to erase the Flash, which is what we're going to do in the first method, or the first thing. Next, we're going to write to Flash, and then the third is we're going to jump to the application. And all of those commands are implemented right over here. That kind of makes sense where it falls into the flowchart? Cool. Any other ones? Yep.
Can you go back to the slide with was it the right array?
This one?
No, not that one, but the one we were at before.
This one?
Can you go to the left? Yeah, what does the go command do?
Yeah, so to reiterate, the go command jumps to the user application code located in internal flash memory. So I have a backup slide prepared with what we actually do in the go command. The go command is 0x21. It checks if protection is active. If protection is active, it's going to tell us, hey, no, you're not going to do anything. Protection is not active. It sends an acknowledgement. And then it basically receives the start address or the address that we actually want to boot for. It checks to make sure that the checksum is all good. And if those two are good, we're going to jump to the user application. In essence, go command is how we actually say, okay, there's some application in Flash. If I write this command, I want you to go ahead and boot to it. Make sense? So it basically implements that like how jump to app function that we saw earlier. This particular implementation is also checking to make sure the checksum is valid. So coming back to that loader consideration of Flash integrity, that's what it's implementing for you under the hood. Any questions on these in particular? All right, so I'll skip over the internals of the S2 bootloader for the sake of time. We kind of discussed about these. I'll just briefly reiterate that in addition to the S2 bootloader having a host, it's also possible for your device to kind of manage its own OTA. So coming back to what Navtaj was mentioning, where they have an SD card, like the CubeSat basically talks to the ground station, pulls the image and puts it in an SD card over here, verifies it, and then can independently choose to launch that image. Just pointing out that you don't necessarily need to follow the earlier pattern of erasing Flash and going wherever. You can also choose to basically make the microcontroller download an image from somewhere. In this case, I chose an AWS server and load it somewhere else. And then you can, at a later time, say, hey, I want to launch this particular image. That concept clear? Cool. One other thing I did want to discuss, because it is pretty essential, is talking about communication safety. And it's not like safety in the sense that you're trying to keep you safe or trying to keep the microcontroller safe. And you'll notice that the ST tool basically calls for checksum. If it receives a block of data, it wants you to XOR it. And a byte containing the computed XOR of all previous bytes is added at the end of communication as a checksum byte. And it claims that by XORing all received bytes, data plus checksum, the result at the end of the packet must be 0x00. The point I want you to take away from this is that when you're talking to a device, it's possible for random bit flips or random communication errors to happen, right? If you've worked with UART for a little bit, or you've worked with I2C or SPI, you'll notice at some points maybe your chip decides to completely interpret a 1 as a 0, for instance, or the other way around. And that can be bad for us. If you come back to here, maybe we actually interpret, this write memory command as an erase because of a random bit flip. So this bootloader calls out the use of a checksum when you're talking to it to basically make sure that every data byte that it receives is actually what you intended to receive. And this is a really common feature that you'll typically implement with any sort of UART.
Just a quick question. Could a bit flip happen in the checksum itself?
Yep, a bit flip can also happen in the checksum itself too. But the important thing is, if it happens in the checksum or the data, you'll still detect it and say, hey, something went wrong here. Answer your question?
Yes.
Cool.
Thank you.
Yep. And then for each command, host sends its byte and its complement is basically saying the same thing over as the above. It's just a 1 byte checksum. Console checksums make sense? Pretty important to grasp that, at least when you're communicating. Cool. So some remarks. Promise it'll get a little less into the weeds now and more high level. Use off-target and hill testing techniques to gain confidence and minimize regressions. Don't be like my friend and push an update that basically breaks the ability for the system to actually update itself. That means that every single customer had to come in to the repair shop, plug in a device with nothing else than a debugger to actually recover it. That costs your company money. In the case of your CubeSat, if you break your update mechanism, you're just stuck with whatever's on there, unless you're going to send someone on like a space shuttle to go recover it. Be very careful when you're developing it. Use off-target and hardware-in-the-loop testing techniques to gain confidence and minimize regressions. If you're going to make your own bootloader with DFU, make it the primary method of flashing, as in if you're going to roll your own bootloader, get rid of all the programmers in the bay except 1 or 2, and constantly use your bootloader to update. This is going to put cycles on it because a lot of the bugs with a bootloader, you're generally only going to find by just testing it constantly. And I strongly recommend writing one yourself with DFU capability. What we've done in this slideshow is kind of discuss the high-level contents and introduce you to what a bootloader is generally doing. And a prerequisite is if you can, generally make a random microcontroller talk to your computer from scratch pretty confidently, you're in a pretty good spot, I think, to investigate making a bootloader yourself. I've linked in the slides a really good tutorial that kind of guides you how to do it on an STM32F7 board. You might be able to find one for your TI board as well that talks it through, or alert the orbital repository. I think you have a functional OTA in there, yeah?
What?
You have a functional OTA in there? In your orbital repo?
Yeah. Over UART, not like over the air.
Yeah, close enough. Yeah, so anyway, I encourage you to make and write your own bootloader just to kind of gain confidence in it. The high-level concepts will translate to any microcontroller family, but I really recommend this particular tutorial. And I've also plugged the bootloader library I wrote with a white paper explaining how I designed it if you're curious about, what considerations you might want to implement. And lastly, I promise I won't take too much time with reliable updates, but it is pretty important to talk about it. And the motivation is, why should you make a DFU system robust? Often it's the only way to flash software in production, again, because you're not going to ship everyone out with a debugger. And you want to prevent devices from entering an unrecoverable state or bricking during updates. You want to provide confidence in shipping updated application software, and all of that means that the way you update your system needs to be rock solid. And I'm curious, now that we've kind of learned the high levels of a bootloader and DFU, what are some things y'all might want to consider in it? Any edge cases, anything we've talked about that's like, what could go wrong in a system? Anyone? Yeah?
If the updates are done over the air, then you probably want some mechanism of making sure that only you are right?
Correct. Yeah, so to kind of repeat that consideration, if we're allowing our device to run code arbitrarily, we're basically saying, hey, we have a way to put random flash into here and run it. We want to make sure that we're the only ones running it. For context, one of the systems I worked on was a steering system for a car. And one of the things we want to make sure is that you can't just make an attacker run random software on a steering system. So it's very important to make sure that if you write a DFU system or allow arbitrary code execution, you have some sort of security measure, like signing, as you mentioned, to basically prevent attackers or unauthorized people from running code on your system. In the case of your CubeSat, I don't think you want someone like taking over your CubeSat by just sending it a random image and saying, yep, my satellite now, bye-bye. You don't want that to happen. Any other considerations that y'all might have?
You might want to explain like what you mean by signing a bit more.
Sure. I'm actually not too familiar with signing. Are you?
No.
Okay. I'll give my best overview. Signing is basically a cryptographic way of attaching some sort of key that you and you alone know to your application. And you basically transmit that to your microcontroller, and your microcontroller looks at this key, does some fancy math using cryptography, and says, okay, I think it was issued by you. And if it doesn't line up with the math, it's going to say, hey, I don't think this application was actually issued by you, and reject it. That's my very high level of cryptography. Are you more familiar with the topic?
I think, yes. Mostly at a high level.
Yeah, I don't fully know the weeds of cryptography. I'm not necessarily a security guy. Look into it if that's what you're implementing for your topic, but signing is the term that you want to look at. Any other considerations that y'all might have for a DFU system in the back?
Ideally, if something goes wrong in the update process, you probably want to just roll back to whatever system you installed earlier.
Yeah, that is an excellent consideration. So if something goes wrong in the update system, we want a way to roll back to kind of like a safe state. And to do that ties in perfectly into this edge case I've discussed. Say you're designing a system with DFU capability and it talks to a host or a USB. So you've got this little Jabra thing, talks to it. And, I'm being clumsy. I jostle the power cable while it's undergoing DFU. So all of a sudden, there's no application flash on it. It was still, trying to update its flash. Halfway through, cable goes dead. No more power. System now reboots with no valid flash to boot into. What should the software do? Any ideas? You've got no valid application flash. Your bootloader is just sitting there like, home.
Ask the host for new image.
Ask the host for a new image? Yeah, that's a possible solution. Any other ones? Stop the bootloader? Yeah, you can just chill in there. You can just basically do nothing. That is also a very valid option. Any other ones?
Keep a copy of the working image and then go back to it.
Yep, that's absolutely. That's also another one. Any other ones? I'm curious. I've got 2 solutions I'm going to present to you, but I'm curious if y'all have any more. There's tons of ways to fix it. Take one more. All right, I'll go in the back once more.
Sort of non-software solution, just like power your device with UPS.
Yeah, sure. Fix the power supply issue. So, make sure there's another power supply if you're going to update. Big red warning label saying if you're going to update it, plug it in with another USB cable, or just be really careful around it. That's an option too. If you go into some product manuals, there'll be a big red warning saying if you are firmware updating your system, do not unplug it. That's because they didn't account for this. And so I'll present to you 2 options. Promise I'll get you out of here in the next 5 minutes. But the first is to scream and kick. Blink LEDs. Let the user know that you failed to update the system. One of the examples that I did was, if I failed to update a bootloader, because I could trust that a user could plug it in or basically click a button to reinitiate. I was like, okay, it's just going to blink purple. Why purple? No one stopped me, so it was purple. And I was like, yeah, I wrote in the user manual, if you see blinking purple lights, please update it again. And that was it, because there was no other requirement to do it except, we wrote in the user manual saying, hey, don't unplug power. Someone unplugs power. Okay, purple LED. Oh, they're on the phone. Oh, there's a purple LED. Okay, reflash it. Cool. Problem solved. Make it easy to diagnose to your user, because otherwise some customer service agent is on the phone being like, what's going on? Kick and scream, make your bootloader say, I failed to update, very concretely. And as Navtaj mentioned, another method you can do is ask the host to retry DFU. So if you already know that something went wrong, you can maybe try asking the host, saying, hey, pretty please send me the image back. And if the host is nice enough, it's going to send it to you. And you can retry it gracefully without the user ever knowing that the DFU ever actually failed in the first place. So that's one solution. And the other one is A/B partitioning, which solves a lot of bootloader problems. But basically, it's that instead of storing just one application on your system, you store two. And you only ever update one application at a time. So the first application you'll load, call it application A. Second application you load, call it application B. The third application that you'll load, say you try to swap out application A, fails for whatever reason. Now, when you want to choose what to boot into after this power loss scenario, application A is completely wiped, but application B still exists. It's perfectly fine. It's just chilling. And so the bootloader says, well, hey, I don't see a valid application A in here, but I do see a valid application B. Okay, let's go into application B. And the user never realizes that their DFU ever failed. And now the next time we ever go to update the software, the bootloader says, well, what application image should I swap? It realizes that there is no valid application A, and then boom, it just loads the flash in. User never realizes that their update ever failed. The advantage of this design is that you will always have a valid application to boot into. Sometimes you might choose to just never update that application. It's always going to be like a safe mode type of copy. If you ever had like a smartwatch or something that's like you hold it down for like 20 seconds, it goes back to this like blank copy that's shipped from the factory. That's basically what they're doing over here. They just have a spare image that's never touched, that they know will work, and you can get into it in some way by like holding a button down. I'm curious if anyone can point out any cons with this design in particular. Let's go in the center over there.
Half as much flash space to work with.
Bingo. You have half as much flash because now you have to store two applications, well, three including the bootloader instead of just two. Any other ones anyone can think of? Yeah?
If you're leaving one of your like applications that are untouched for a long time, it could get corrupted. Especially if you're relying on this, then if it gets corrupted, you're screwed if you don't have other mechanisms.
Yeah, that's actually a good one I hadn't thought of. So problem you mentioned is that, say if you have the safe mode strategy, right, and you just kind of like leave it chilling, for a few years, and then, all of a sudden the watch fails. So pressing down on a button for a few seconds, and it tries to boot into this other application. But wait, there's random bit flips everywhere because it's been a few years. Maybe you're not going to be able to boot into that application anymore. And now you no longer get the pro of having a nice, safe application that the user can boot into, and you're stuck in the bootloader. Yeah. Any other ones? Hardy, and then you.
Maybe there's a possibility that the user could, or the bootloader could screw up both of the image.
Yeah, small possibility, but that's the case. So you mitigate that by doing lots of testing, a lot. But yeah, there's a case that you actually screw up both images for whatever reason, or there maybe is a common bug in both images that basically corrupts them both. So that's also an option too.
Related to Harry's response, let's say there's two images that's already on the microcontroller, image 1 and image 2. And then now we want to flash image 3, and because we don't have a lot of flash space, we can overwrite one, like let's say image 1. DFU fails, so the bootloader can't load image 3, and now it only has image 2 to load.
Yep.
What happens if it turns out image 2 is a slug?
Yep, that's a very good thing.
Even if you want to copy something, the best way to do is just copy that buggy image to over.
Yep.
To that same microcontroller.
Yeah, so that's correct. The other thing with A/B partitioning is if you have a bug in an application, like say you have this old firmware update, application B is some random old software, or application C that you meant to replace application B was fixing a bug in application B. Maybe if like you pass like a certain day, stuff just explodes, but you no longer get that valid application C, then you're going to hit that bug in application B. So it's very important to be mindful of introducing bugs into your system, and especially knowing that you might boot into them if you're not careful. So yeah, if you have like a ticking time bomb left in an application, A/B partitioning won't solve it, and in fact can increase a user's exposure to that bug. Cool. All right, and the last slide I'll leave you with today is a case study. BMW had this thing going on. I'll see if I can zoom in for y'all in the back, where it basically refused to update the car because it was too steep. BMW's engineers commented that they would not allow a software update of the parking brakes if the slope of the hill was more than 7 degrees. And the rationale that they gave was because if the parking brake fails, what's going to happen to the car? So pretty bad consequence. If you start to work in industries like automotive, aviation, and your loader has the ability to do this, the first thing is your loader is now safety critical because you do it the wrong way. You're watching your car, watching TikTok or whatever. Parking brake suddenly fails. You're now rolling down a hill. There's a very good chance the occupant dies. So important thing is if your loader has the ability to kill someone or do something very serious, there's a chance it might be subject to safety critical regulations. Double check that with someone who's experienced with it because I'm not. But that being said, BMW didn't allow OTAs on inclines greater than 7 degrees because they looked at that and said, hey, we have a risk where if the OTA fails on the parking brake, there's a chance the parking brakes might release, paraphrasing a little bit. And because there's a chance that the parking brakes release and the grade is more than 7 degrees, the car might roll. And 7 degrees is actually not that much. It's like basically flat. And so I'm curious to y'all, what are some solutions to this problem that you might be possible to implement in a bootloader? Anyone? Get creative. I have one that I thought of on my way, but it took me a few minutes.
You could load the program to like volatile storage and then only transfer over to it once like the grade is reasonably flexible.
Oh, that's actually pretty creative. So the solution you're mentioning is basically load it into RAM and then maybe tell the user to drive somewhere steeper before rolling it. So maybe you don't need to pay the cost of actually transporting the data. That could be one thing you could do. Yeah?
You could have a redundant microcontroller that doesn't get updated that can handle the parking brake while the other one's being updated.
Yeah, that's a good thing. So redundant microcontroller architecture, if your hardware has 2 micros, maybe you basically say for the duration of an update, you hand control to the other micro, update it, and then do some sort of locking to make sure they both get updated correctly. And one always has control of the parking brake. Any other ones? Yep.
You can also do like a more traditional electromechanical solution. Like if you want the car to update, you can tell the user, hey, set the parking brake manually. After it detects it starts to update. Because the parking brake was set manually, it will not roll. And after the update ends, it will tell the user to release the handbrake.
Yeah, that's also possible too. So if you have access to a manual handbrake, maybe being like, well, if you're on a hill, make sure that manual handbrake is set before starting an update. So yeah, all very good solutions. My solution was like, well, if you have 4 parking brakes, or if you have 2, just update one, make sure that one's successful, then update the other. Kind of like Navtaj's solution of 2 hardware cores that only get updated independently to make sure the parking brake doesn't release. And I believe that's actually it for the case study and the bootloader slides. Any general questions I can answer about the topic? Bootloader, DFU, OTA, any clarifications? I know it's a lot of content. I didn't get as much into the weeds as I hoped to, but I don't want to bore y'all. Any other questions I can answer?
Yeah, I'm still having concerns about what the purpose of multiple level bootloaders are because I don't know.
Cool. So to answer the question about multiple level bootloaders, one thing that we might desire to do is to actually update the bootloader itself. So we've got a bootloader. It can update. Great. We can load arbitrary applications. But maybe the time comes along where we find a bug in the bootloader, or we want to, make an improvement to it. And we want to be able to update the bootloader itself. And so what a multi-level bootloader allows you to do is you have a small micro loader, as it's called, that'll allow you to load into a second stage bootloader. And this second stage bootloader can now load in another application, or it can download an application to update the bootloader explicitly. A multi-level bootloader allows you to do this by basically allowing you to overwrite Flash in a safe way without getting rid of the actual OG bootloader. And the reason is, if you have no valid Flash at the base address, the microcontroller is going to boot into nothing. That's why if you want to have a self-updating bootloader, you will typically see two bootloaders being used. One bootloader that is always there that you never update, that basically ships from the factory. It's very simple, and its only job is to load another bootloader. And then you have a second stage bootloader that actually does all the fancy processing. And the way you recover a device with the second stage bootloader is, say your second stage bootloader gets wiped while you're updating it. You can now have a repair tech plug into the first bootloader with, say, a lightning cable or USB-C cable rather than a programmer to recover the device. So instead of needing to send every tech out there with a debugger, you just say, okay, plug in a USB cable, or you tell the user to go online, download something, plug it in, and recover the device with the microloader. Does that answer your question? Cool. Any other ones I can answer on the topic in general?
So on the startup of the board, do you want to boot into the bootloader every time, or do you want to boot into the app and only boot into the bootloader when you're doing an update?
So for most microcontrollers, you're not given a choice. You're going to boot into the bootloader.
Okay.
Now, the question of what you want to do after is your decision. Some applications, maybe you want to be like, okay, you have to press a button in order to go to the application. Some applications are going to say, hey, you're going to wait 1 second. And if you don't hold down a button in 1 second, we're also going to go straight to the application. But if you hold the button down, we're going to wait. We're going to do nothing. Kind of like how you load into your BIOS by like holding down F11 or whatever. So it depends on your system, whether you want to load into your application directly, whether you want to wait for some sort of input. It depends on what you're working on. But does that kind of make sense as to like the decision is yours, but you'll always boot into the bootloader first, and the bootloader makes that decision?
Yeah. So is there like a way to like communicate values between the bootloader and the application?
Yeah, so I did mention it a little bit where you can have a section of persistent RAM. Persistent RAM is basically a section of RAM that you tell the bootloader to never clear out and the application to never clear out. And then both the application can write to this section of RAM and the bootloader can also write to this section of RAM. And both of them can kind of read it independently. This solution works if you don't care about power on resets impacting stuff. Like if you have a power on reset while you're in the application, then the bootloader won't see any of those contents. But if you just dedicate a section of RAM that neither the bootloader or application clear out, both of them can write stuff to it. And you can communicate stuff between the bootloader and the application in that way.
Okay, so you want to do like a automatic software update that gets loaded from the application. So you send the binary from like to the application.
Mhm.
And the application writes to an SD card.
Yep.
Then you would write to that like shared
Mhm.
memory space, and then like tell the bootloader on the next reset, look at that value and see if there's a new version.
Yep.
Boot. Okay.
That's that's a very valid way of doing it, in implementing your DFU in the application. So application will just read to the SD card. SD card does its fancy stuff. You tell the bootloader, hey, next boot, you're going to boot from the SD card. Is that a valid way to do it?
Also, I was gonna add for Orbital, like we have the FRAM for stuff like this. So, like for example, when the application writes a new update binary to the SD card, it can write to the FRAM like a flag that says update available, and bootloader can check every time it starts up for that flag to see if an update's available, and when it does an update, clear that flag so that it knows based on that flag whether or not there's an update or not, or if it should boot straight into the app.
Okay.
Cool. Any other questions? Yep.
How does this work with a protocol like SWD? Like, is that also like calling programs in Flash, or is that?
So SWD is a debug-specific protocol. All these protocols like SWD, JTAG, or whatever, they actually access like a separate hardware variant, like hardware section of the chip. It doesn't talk to any sort of bootloader or whatever. It activates physically different silicon. And so you won't be implementing a bootloader through SWD or through JTAG. You're physically activating a different part of the chip to flash and do anything with it, if that makes sense. So it's not a protocol used for bootloading because it's meant for programmers and debuggers. Cool, I'll take one more.
What's like the sort of pros and cons of validating data by one using XOR and two using CRC?
That is a good question, and one I'm going to take the cop-out answer to, where there's an excellent book by Philip Koopman called Understanding Checksums and CRCs. The one thing I'll say is read it if you're interested in that, because I know nothing about it, and I've been told if I want to learn anything about it, read that book, because he is the checksum guy. So Philip Koopman, look up Understanding Checksums. The answer will be in there. Cool. All right, I did promise that would be the last one just because I want to get you all home. It's 10 p.m. Thank you so much for coming out. I'm in the Orbital Discord and Work Discord if you want to reach out to me. Slide deck is also here. There's a little bit more content and all the links are there. And also there's some stuff in the speaker notes too. In the meantime, have an excellent evening and I'll be around if you want to answer questions. Thanks.